Now, under chemical properties of ethers, we have two important chemical properties to be discussed. First is reaction of ether with hydrogen halide, that is with hydrogen iodide or hydrogen bromide. And second chemical property is electrophilic substitution reactions of ethers. These ethers are the least stable functional groups or least reactive of the functional group. So, the properties, chemical reactions of ethers takes place under drastic conditions. Let's discuss the first chemical property of ether, that is, the reaction of ether with hydrogen iodide. Reaction with hydrogen iodide. Now, I have written 5 examples on the board. Reaction with hydrogen iodide. Now, the examples are written on the board. Now, the product formed when ether reacts with excess of hydrogen iodide is alcohol and alkyl halide. Now, look at the first example. C2H5O C2H5 plus HI. Now, you can see this is a symmetrical ether. Symmetrical ether means the alkyl group on either side of oxygen atoms are the same. So, this is a symmetrical ether. When this reacts with HI, we get the product as alcohol and alkyl halides. Now, since this is a symmetrical ether, any one of the alkyl group can go as alcohol and the other will go as alkyl halide. So, the product formed is C2H5OH alcohol plus one alkyl group will go as alkyl iodide C2H5I. Now, you can see the reaction of ethers with hydrogen halides involves cleavage of carbon-oxygen bond. The carbon-oxygen bond is broken and we get the product alcohol and alkyl halide. Now, this is with symmetrical ether. Now, with unsymmetrical ethers, when they react with excess of hydrogen iodide, we get alcohol and alkyl halide. But which group will go as halide and which will go as alcohol depends upon the type of alkyl group attached to oxygen atom. Because we know in unsymmetrical ether, the two alkyl groups attached to oxygen are different. So, it is said that if one of the alkyl group is methyl and the other alkyl group is a primary or secondary alkyl group, then the methyl group will go as alkyl halide and the primary or secondary group will go as alcohol. Look at the second example. This is an unsymmetrical ether, CH3O C2H5, and the name of this ether is methoxyethane plus hydrogen iodide. And we know one group is methyl group and the other is a primary alkyl group. This is a primary alkyl group C2H5 because this is OCH2 CH3. So, oxygen functional group attached carbon is attached to one other carbon atom. So, this is a primary alkyl group. And I told if it is a primary alkyl group, then the methyl group will go as halide. So, we get CH3I. And here the CO bond broken is this, CH3O bond is broken and the other group, primary alkyl halide will go as alcohol, C2H5OH. Now, look at the third example. Here we have CH3O, CH3 twice. Now, here again, one group is methyl group and the other group is CH3 twice, which is a secondary alkyl group. This is a secondary alkyl group because the oxygen attached carbon is attached to two other carbon atoms. So, methyl will go as alkyl halide, we get CH3I. And this group will go as alcohol, CH3 twice, CHOH, which is a secondary alcohol. Now, these two reactions take place by Sn2 mechanism. That is, the reaction of unsymmetrical ether with hydrogen halide, in which one of the alkyl group is primary or secondary, will take place by Sn2 mechanism. That is why we get one product, that is the lower group, go as halide and the primary or secondary alkyl group going as alcohol. Now, if it is a tertiary alkyl group, that is in the unsymmetrical either, if one of the group is methyl and the other alkyl group is a tertiary alkyl group, then we get alkyl halide and alcohol, in which the tertiary alkyl group will go as alkyl halide and the lower group, that is the methyl group, will go as alcohol. Now look at example number 4. CH3 thrice COCH3. This is the methyl group and this is the tertiary alkyl group, that is CH3 thrice C plus HI. Now if it is a tertiary alkyl group, this will go as halide, CH3 thrice Ci, and the lower group, methyl group, will go as alcohol. Now, the reason for this is the tertiary alkyl group will undergo the reaction with HI by Sn1 mechanism. And we know in Sn1 mechanism, it involves the formation of a carbocation. And we know that a tertiary carbocation is more stable and it is more reactive towards Sn1 mechanism. So, the tertiary carbocation will immediately take the nucleophile I- from HI and we get a tertiary alkyl halide as the product and methanol as the alcohol product. So, whenever the products are to be written with hydrogen iodide, either with hydrogen iodide, we should check, and if it's an unsymmetrical either, we should check the alkyl group present. If the alkyl group present is a primary or secondary alkyl group, they will go, the primary or secondary alkyl group will go as alcohol and the lower alkyl group goes as alkyl halide. If the alkyl group is a tertiary alkyl group, then tertiary alkyl group will go as alkyl halide and the lower alkyl group will go as alcohol. Because if it's a tertiary alkyl group, the mechanism is Sn1. And if it's a primary or secondary, the mechanism is Sn2. Now, example 5 is with a phenolic ether. That is our phenitol, C6H5O, C2H5 is phenitol. Now you can see phenitol with HI. I told you the reaction of either with HI involves cleavage of carbon-oxygen bond. Now in this case, here we have a carbon-oxygen bond and also we have a carbon-oxygen bond here. Now here it is this bond, that is the alkyl oxygen bond, that breaks. And we get C6H5OH, that is phenol, plus C2H5I. So with phenolic ether, the reaction with HI, the product is always phenol and alkyl halide. Now it is phenol because this bond, I told you it is the OC2H5 bond that breaks because this bond is weaker than the carbon-oxygen bond. This carbon-oxygen bond. That is because this bond, this carbon, it is sp2 hybridized. Also, we can see that in the resonance structure there is a partial double bond character coming for this phenyl oxygen bond. As a result, this bond is little more stronger than OC2H5 bond. So this will break fast and we get phenol and ethyl iodide as the product. So phenolic ethers with HI, the product is always phenol and alkyl halide. Now the example 6. Example 6 is a benzylic ether. Benzylic ether. Now, example 6 is with a benzyl ether, benzylic ether. You know the formula of benzyl alcohol, C6H5CH2OH. Benzyl chloride, C6H5CH2Cl. Now, this is benzyl ether, that is C6H5CH2OC2H5. Or the name of this compound is benzyl ethyl ether. Benzyl group is C6H5CH2. Now functional group is ether. So benzyl, ethyl, ether. When this reacts with hydrogen iodide, the product formed is, instead of benzyl alcohol, we get benzyl iodide as the product. So C6H5CH2I plus C2H5 will go as alcohol. Now here the reason is the mechanism involved is again Sn1, and the benzylic carbocation is more stable due to resonance structure. So the benzylic carbocation will immediately take the nucleophile I minus from Hi, and we get benzyl halide plus alcohol as the product. And the name of this compound is benzyl iodide, C6H5CH2I. So this is the reaction of ethers with hydrogen iodide. That is the symmetrical, let it be any either symmetrical or unsymmetrical, the product formed when either react with hydrogen iodide is alcohol and alkyl halide. If it is an unsymmetrical ether, the product, whether it is alcohol, who will go as alcohol and alkyl halide is decided by the alkyl group present in ether. If one of the alkyl group is methyl and the other is primary or secondary, the methyl group will go as halide and the primary or secondary will go as alcohol. If one of the alkyl group is methyl and the other alkyl group is tertiary, then tertiary group will go as halide and methyl group will go as alcohol. Now with phenolic ethers, the product formed is always phenol and alcohol. And with benzylic ether, the product formed is benzyl halide and alcohol. With this, the reaction of ethers with Hi is over. Now, the second chemical property of ether is electrophilic substitution reaction. And for that, let's discuss the resonance structure in ether. Now, in ether, the alkoxy group, that is RO group in ether, is ortho-para-directing. Means it can activate the benzene ring towards electrophilic substitution reaction and we get two products, ortho and para products, same like phenol. That is because in the resonance structure, we can see that there is more electron density at ortho and para position. So, I am going to draw the resonance structure of ether. This is the ether molecule. Now, there are two lone pairs on oxygen atom. One lone pair will get shifted to this position, double bond gets shifted to this position. So, I am going to draw the second resonance structure, that is, here we get a double bond with OR and a positive charge on oxygen with a lone pair, and here we have an electron with a negative charge. Now, in the next shift, this will get shifted to this position, this gets shifted to para position. So, the third resonance structure is double bond OR with a positive charge oxygen and the electron at para position. Now, in the next resonance structure, this will get shifted to this position, this again to ortho position. So, the next structure is double bond O with positive charge and the electron at the next ortho position. Now the last shift is this electron getting shifted to this position, double bond go back to oxygen. So the final structure, resonance structure is now you can see from the resonance structure there is more electron density at ortho and para positions of the ring. Ortho position, this is one ortho position. Now this is the other ortho position, this is the para position. So the incoming electrophile can come and easily attack ortho and para positions, and this ethers when treated with electrophiles or when they undergo electrophilic substitution reactions, we get ortho and para products. Now we are going to discuss the examples for electrophilic substitution reactions in ethers. First is halogenation, and we know how is halogenation done. Halogenation. In halogenation, either is allowed to react with halogen. Now here, instead of taking anhydrous aluminum chloride, that is our Lewis acid, we can take halogen in presence of acetic acid. So I'm going to write the equation, that is halogen in presence of acetic acid. So I'm going to take anisole. The formula of anisole is C6H5OCH3 plus halogen bromine in presence of acetic acid. Here the electrophile is bromonium ion getting attached at ortho and para position. So we get two products plus this is ortho-bromoanisole and this is para-bromoanisole, and always para is the major product. Now the next reaction is nitration. Electrophilic substitution reaction is nitration. So in nitration, again I'm going to write the example with anisole. We take concentrated HNO3 plus concentrated H2SO4. And in nitration, the nitronium ion will be attacking ortho and para position. That is NO2. And always para is our major product. Now, the next example is Friedel-Crafts Alkylation. The name of this compound is orthonitroanisole and this is para-nitroanisole. Now, next is Friedel-Crafts Alkylation. And alkylation is done using alkyl halide in presence of anhydrous aluminum chloride. So, again, anisole plus CH3Cl in presence of anhydrous aluminum chloride. Now, alkyl group is introduced at ortho and para position in Friedel-Crafts alkylation. OCH3 CH3 plus and this is the major product. Now the last example is Friedel-Crafts Azylation. Fourth example is Friedel-Crafts Azylation. I'm going to write the example with acetic anhydride CH3CO twice O. Now instead of using acetic anhydride, you can also take acetyl chloride in presence of anhydrous aluminum chloride. The acetyl group is introduced at ortho and para position. So the product is OCH3 COCH3 plus and always para is the major product. Now, when you name this compound, you have to number. There are two functional groups in this compound. One is ether and the other is keto group. So, either group should be given the highest number and keto group should be given preference, that is it should be given the lowest number. So, here this will get number 1, this has 2. And here 1, 2, 3, 4. Now you know if there is no OCH3, this is acetophenone. The compound C6H5 COCH3 is acetophenone. Now the name of this compound is 2-methoxyacetophenone and this is 4-methoxyacetophenone. And you have no sulfonation reaction to study. for ethers. So these are the 4 electrophilic substitution reactions given by ether. Halogenation. Halogenation takes place in presence of acetic acid, not in the presence of anhydrous aluminum chloride. And second is nitration. Third is Friedel-Crafts Alkylation. Fourth is Friedel-Crafts Azylation. So with this, we complete the chemical properties of ethers. Thank you.